Good morning, everyone. Nice to see everybody's faces. So let's talk a couple of reminders real quick. Quick reminder. So again, I'll be back tomorrow, and I'll be back Wednesday, Thursday, and Friday, which basically means that, again, we'll have a virtual class on Wednesday next week. Okay. So other than that, today we're going to start chapter 28. So chapter 28, which will officially be the last chapter for the upcoming exam. And again, that's, remember, 1 week from tomorrow. So this one, we're going to start putting together resistors into parallel and series, basically the same thing we did with capacitors. And then we want to look at multiple batteries and all kinds of different stuff. But the first thing we're going to talk about is, so before we talked about a battery, so again, we said a battery's purpose is to supply a constant potential difference across the battery, so that way it can actually do work onto the system and then move charges. So here we're going to talk a little bit about terminal voltage. So terminal voltage is the voltage which is then measured when you go across the battery. So here we're going to measure then the potential difference between point A at this point here, and then point B, which is on the other side of the positive terminal. So here, for an idealistic battery or an ideal battery, we always have that the potential difference going from A to B, which is equal to is always then equal to that of the EMF, regardless of how much current we're actually going through it. But as you guys now know from lab, if you actually measure the potential difference across the battery when there's no currents running across it, in that case, when there's zero currents, you do measure exactly the EMF, but once you apply it to a circuit and you start running current through the actual system, in that case, the potential is not equal to the EMF anymore, but it actually drops a little bit. So this is actually a realistic battery. And we talked about this in class. So again, the reason for that is that you're trying to dissolve one of these terminals and then strip electrons off the other one to then neutralize the electrolytic solution, which basically takes time, which causes this thing to have a potential drop. So typically, the way that we're going to deal with a realistic battery is we're going to say that a realistic battery is actually a EMF. So again, we have our EMF, but this is going to be attached then to an internal resistance, which then has a resistance of then little r. So basically, this entire thing then is going to be our battery. So we're going to model that slow flow of electrons being pulled from then the positive terminal into the electrolytic solution, and the slow dissolving then of the negative terminal as then being an internal resistance, which can never be disassociated with the battery itself, which basically means that here and here, so if this is our point A and this is our point B, then our potential difference going from A to B is then going to be equal to the EMF minus then the current times this internal resistance. So basically, a realistic battery then is just, again, a battery or an EMF in series with little r, which is what's known as the internal resistance. So again, the internal resistance, we can never uncouple from the battery itself. It's always going to be there. So again, if there's no current actually running through our system, so in this case, if the current is equal to 0, then VBA is going to be equal to E minus 0 times R, which is simply equal to that of the EMF. But then when current actually runs through the system, so when this is not equal to 0, then our potential difference, BA, will be equal to E minus I times R, which will be less than that of the EMF. So this is how we actually model then a realistic type battery. Okay. Now, this also gives us one piece of information, which is that if I had, this is my point A, and then this is my resistor, point B, what this thing is also saying is if we have current, say, running in the direction from A to B, so current is running this way, which is what it would be doing in this case, going in this direction. What that means then is that there is a potential drop across the resistor. So the potential difference between points A and B is then equal to negative the current times then the resistance of the resistor. But if I go the opposite direction, So if I go from B to A, in that case, I have to have a potential gain going in the opposite direction. So here I'm going to get a plus IR. So it should actually be BA. There we go. So AB. So in this case, if I'm going in this direction, so this would be the green line. If I go this way across my resistor in the same direction as the current, I have to have a potential drop, meaning the potential at point A is greater than the potential at point B. So this is my green arrow. But if I go the opposite direction, say the yellow arrow, so if I go from B to A, so I'm going in this direction, I have to then have some potential increase because again, the potential at B is less than the potential at A. So the point of this is to say that the point of putting a resistor into a circuit is to cause a potential drop. So that way we can abide by conservation of energy. So that way when we have a battery connected to a resistor, so that way we have enough potential drop going back to the battery, so that way we preserve conservation of energy. So the change of potential is equal to 0 throughout the entire loop. Okay. So good. So the next thing we want to talk about is how do we add resistors in parallel and series? So resistors in parallel and series. So the reason we have to do this is exactly the same reason we have to do that with capacitors, is because, again, manufacturing speaking, I only want to make a certain amount of resistors. I can't make the infinite spectrum of resistors that somebody's going to need. So we can only make a few handful of resistors, and then from there, learn how to combine these guys together to make the resistance that we want. So again, we're going to look at our two different scenarios. So we have parallel. So in parallel, we have our battery. So here's our EMF, and that's going to be attached to, say, 3 resistors. So I have this one, and then this one, and then that's attached to this one. And then that's going to be connected back to then the battery. So again, this is our parallel. So this is our potential. This is R1, R2, and then R3. And then in series, we're just going to connect these guys directly to each other. So here is my battery connected to a resistor, connected to a resistor, connected to another resistor. So here I have R1, R2, R3, and then my potential. Now, same thing we did with capacitors. Our claim is that we can combine both of these two situations down so that we have one battery connected to a single resistor, which is what's called the equivalent resistor. So this is our claim. So our claim is we can combine all 3 of these resistors down to make an equivalent resistor. Or in this case, we can combine all of these down to make an equivalent resistor. So both of these two will combine down to this equivalent circuits. Now, just like for capacitors, what's true is in parallel, the voltage is the same, which means that the potential difference across 1 here is exactly the same as the potential difference across 2, which is the same as the potential difference across 3. So here we have to have that delta V1, there we go, is equal to delta V2 is equal to delta V3. But in series, what's now is that the current has to be the same. So for capacitors, we had to have the charge was the same because the charge actually goes to 0 for capacitors, or sorry, not the charge, but the current goes to 0 for the capacitors. But here, when it comes to resistors, we constantly have current flowing through our system, which means that the current, which is flowing through resistor 1, the current which is flowing through resistor 2, and the current which is flowing through resistor 3 must all be the same because there's no junction points, there's no nodes, there's nothing which causes the current to go in different directions. Unlike here, where this junction point here and this junction point, or this node and this node, causes current to move in then different directions. So when it comes to the series, what has to be true is that current I1 must be equal to current I2, which must be equal to current I3. Okay. So let's analyze these two systems and let's find out how to actually combine these things together. And again, using the fact that the potentials here for parallel have to be the same and the currents here for series have to be the same. So let's do that. So which one do you want to do first, series or parallel?
Parallel.
Parallel. Sounds good. Let's do parallel. Watching everybody eat their breakfast is making me hungry. Okay, so good. So let's do the parallel one first. So here is our potential connected to, again, let's put one up here. So this is R1, R2 here, and R3 here. Good. So again, what has to be true is that our potential across 1 and our potential across 2 and our potential across 3 must be the same. But since in general, R1 is not going to equal R2, which is not going to equal R3, then that means the currents which come through each one. So the current running through R1, the current running through R2, and the current running through R3 must all in general be different. But what comes out of the battery is a current, which is going to be dictated by the overall resistance of our circuit. But since some of the current from this I is going to go through here, some of the current's going to go through here, and some of the current's going to go through here, then it has to recombine back together to go back to the same current on the other side, charge conservation. What that means then is that the current I1 plus the current I2 plus the current I3 have to equal the total amount of current coming through the system. So in this case, what we know is that, let's go back forward. Here, I must be equal to I1 plus I2 plus I3. So this has to be true. So the amount of current coming out of the battery must be equal to the sum of the 3 currents going through each one of these resistors. Now remember, Ohm's law says that the change of potential is equal to the current times the resistance, which means we can say the current then is equal to the potential divided by the resistance. So the right-hand side I can rewrite then as potential delta V divided by R1 plus delta V divided by R2 plus delta V divided by R3, and that's all equal to I. But I, again, is dictated by the total amount of resistance, or the total amount of resistance in this case is simply equal to Req. So that means that this current coming out of the battery here, I, is the same which is coming out of this battery here, I, which is dictated by the overall resistance Req, which means in this case that I is simply equal to the change of potential divided by Req. Now, since all of these guys are in parallel, that means that this change of potential here is the same as all of these change of potentials, which means they can just cancel out. So let's go ahead and cancel those. So finally, what this tells me is that 1 over Req is then equal to 1 over R1 plus 1 over R2 plus 1 over R3. Or in general, this is then equal to the sum over I of 1 over Ri. So this says that whenever we have resistors which are then in parallel, we then have to add them inversely together. Now, this is actually the opposite of what we had to do for capacitors, where in capacitors, when we had them in parallel, we simply added them together. Now, when we talked about capacitors, we also mentioned that if we add them inversely, what this does is it then decreases the overall resistance. So decreases overall resistance. So if I want to decrease the resistance or have a resistor which is less than any of the other resistors that I then have to add them all together in parallel to decrease the amount of resistance. Now the reason for that goes back to, remember that resistance is equal to resistivity times the length divided by the area, which means if I add them in parallel, I'm effectively increasing the area. As I increase the area, then my resistance goes down. So what I'm doing here is I'm increasing the area, causing the total resistance then to go down, okay, by adding them in parallel. Everything's okay? Not too bad. Good. So let's now look at series. So in series, so again, here's my battery connected to R1, connected to R2, connected to R3. So here's my battery, R1, R2, R3. And again, what has to be true is that the current which is coming out of the battery, I, must be the same as the current going through R1, the same as the current going through R2, and the same going through R3. Because again, in series, everything has to be the same by charge conservation or current conservation. Now, since this has the same current, but it has in general a different resistor, that means then that the potential difference across 1 is in general different than the potential difference across 2, which is in general different than the potential difference across 3. Now, what has to be true though is that the potential drop from 1 plus the potential drop from 2 plus the potential drop from 3 must be equal to the potential gain given by the battery. So in this case, we then have to say, well, the battery potential must then be equal to the potential drop from 1 plus the potential drop from 2 plus the potential drop from 3. So this has to be true. Again, Ohm's law tells us that the potential is equal to the resistance times the current. So I can rewrite this then as the current times the resistance 1 plus the current times resistance 2 plus the current times resistance 3. And again, our claim is that this thing will drop down and become one equivalent resistor. So REQ here, where this is V. But again, this current coming out of here must be exactly the same as these currents flowing through these resistors, which means the current through this equivalent resistor must be the same. So this potential drop across this resistor must be equal to the potential gain from the battery, which means it has to be the same as the sum of these 3 potential drops. So from here, I then have to have that the current times the REQ must then be equal to the sum of the current times the resistances. But again, since all these currents are the same, we can cancel out all these currents. And finally, what we get is that the equivalent resistance is then equal to the sum over all these resistors. Or again, in general, this is simply the sum over all resistors. So again, as we talked about before, since I'm adding all these together, the overall effect of this is to increase the overall resistance. So if I need a resistance greater than all of the resistors that I have, I then simply sum them all together, and then that's going to give me a resistor whose resistance is greater than each individual resistor. Put it that way. Okay. Now, again, the reason for this goes back to, again, R is equal to rho times L times, or divided by the area. So here, when I add them in series, I'm effectively increasing the length of each resistor. So in this case, we're increasing the length, which has the overall effect of increasing the overall resistance. So this is the reason why the resistance overall increases. So good. So let's recap all this. So here I'm going to write down for capacitors, just to remind us for capacitors. And then here we'll write down for resistors. So if I do parallel and series. So in parallel for capacitors, we simply sum them together. So CEQ is equal to the sum of all the capacitors, so CI, and in series, we add them inversely. So 1 over CEQ is equal to the sum of 1 over all the capacitances. For the resistors, it's the complete opposite. So when I have resistors in parallel, 1 over REQ then is equal to the sum over all of the inverted resistances, and the series REQ then is equal to the sum over all the individual resistors. So again, these things are just opposite from each other. So ultimately, if you remember one of these combinations, then you can get the other one by just noting that it's the complete opposite. So again, what's the same? So here for capacitors, what's the same is in parallel, it's voltage. For series, it is charge. For resistors, again, in parallel, it's voltage. And for series, it's moving charge or current. So this is all the same. So these are the quantities that are the same. So the way we analyze these problems is exactly the same way we analyze those for the capacitors. Is when I give you a circuit, we then have to collapse everything down into one equivalent resistor, going step by step, noting what was in series, what was in parallel, and then find the overall equivalent current from the equivalent resistance, and then unravel everything that we just did to then find everything that we want. Okay. So again, these problems are nice and easy. They're just kind of tedious at the end of the day. So let's do an example. So this example says, in the circuit below, what is the equivalent resistance? What are the currents flowing through each resistor, and how much power is delivered by the battery, and how much power is lost by each resistor? So this is what we want to know. Okay. So let's draw our circuit here. Bring up a cheat sheet so I can remember. So good. So let's redraw our battery. So here we have our battery, V, which has 120 volts worth of potential. That's connected then to resistor R1. So this is R1, which is then connected to R2 and R3. So this is R2, this is R3, and these come back together and then connected back to the battery. So this is our circuit that we want to analyze. So plus side, minus side. So here we're told that R1 is equal to 400 ohms, R2 is equal to 500 ohms, and then R3 is equal to 700 ohms. Okay. So what do we want to know? So here we want to know is, what is REQ? That's the first thing we want to know. We also want to know what's the current through each resistor. So since I have 3 resistors, I have to have 3 currents. So I want to know what's I1, what's I2, what's I3. So I want to know all 3 of those. I want to know how much power is delivered by the battery. So I want to know power from the battery. And then I want to know how much power is lost by each of the individual resistors. So I want to know power lost by 1, power lost by 2, and power lost by 3. So these are all the individual things that we want to know. Good. So good. Whenever we do these problems, the first thing we have to do is identify what is in series and what is in parallel. So first thing we want to do is look for the locations of the junctions or the nodes.
Daddy, do you know where my tablet is?
Yes, it's downstairs on the pantry. Your sister was playing with it earlier.
And where is it now?
It's in the same place. Okay. Can't live without our tablet. Okay, so good. So the first thing we want to know is what is in series and what is in parallel. So what's in series and what's in parallel?
R2 and R3 are parallel. And
which ones are in parallel?
R2 and R3.
Good. So we know that R2 and R3 are in parallel. So first thing we're going to do is go ahead and combine these guys down. So let's do that. So let's draw a new diagram. So here again is our battery connected to R1. Good. Which is now connected to a new resistor. Let's call that R23, which is then connected here. Good. So now R1 and R23 are connected in series. Good. So these guys are now connected in series. So finally we can combine these together to then create our, so let me draw it over here. So here's my EMF connected now to simply REQ. So here's REQ, and here again is our battery. Good. So to find REQ, first thing we note is R23 are 2 things in parallel. We know to add them in parallel, we have to add them inversely to each other. So we can then say R23 is then equal to R2 times R3 divided by R2 plus R3. Right. So this is then going to be what, 500 times 700. Good. Divided then by what, 1200, right? No, not 12,000. Too many zeros. There we go. So 1200. So these zeros will cancel out this one. So good. So that gives us that guy. And then finally, REQ is then going to be equal to R1 plus R23. So that's going to be equal to 400 plus the result of that, which then works out to be 691.67 ohms. So this means this is 291.67 ohms. And then plus 400 is then 691.67 ohms. So this is then the equivalent resistance. It was okay? Not too bad. Good. So the next thing we have to do is now go backwards. So now we're going to start here and then go backwards. So we see that this REQ came from two resistors which were connected in series, which means what has to be the same is the current. So the current flowing through this one has to be the same as the current flowing through this one, which has to be the same as the current flowing from this battery, which means that this current flowing through here, which is IEQ, must be the same as this current here, IEQ, which is the same as this current IEQ. So the first thing we then have to do is find out what is IEQ. Good. So to get IEQ, we're just going to use Ohm's law. So Ohm's law then says that our potential, which is the potential out of the battery, must be equal to the current, which is IEQ, times the resistance REQ. So this means then that the current IEQ is then equal to our potential divided by REQ. So this is then equal to 120 volts divided by 691.67 ohms, which works out to be 0.173 amps. That's okay. Now again, let's go back. So from our picture here, that means that the current running through R1 is the same as that. So IEQ and I1 are the same. And then the current running through R23 is also equal to IEQ. So from here, we can now automatically write down that I1 is equal to IEQ, which is equal to 0.173 amps. So the amount of current running through resistor R1 is that of the equivalent current, which is 0.7173. There we go. If I could speak, life is great. Numbers okay? Good. So now what I know is, let's go back to our picture. I have the current going through R23, but R23 came from two things which were actually in parallel. So these two came from these two, which were in parallel. And what I know is in parallel is the potential is the same. So what I know is the potential across resistor R23 is the same as the potential across resistor R2, which is the same as the resistor R3. So now we need to figure out what is the potential across 2, 3, because the potential across 3 is that same potential, and the potential across 2 is that same potential as well. So now let's determine how much potential is going through or across that particular resistor. So Ohm's law tells us that the potential across 2, 3 is then equal to the current across 2, 3 times the resistance 2, 3, which is then equal to the equivalent resistance, or sorry, the equivalent current times then resistance R2, 3. So this is then equal to current 0.173 amps times the resistance, which was 260, what was it, 61? Oh, sorry. I knew how to do math. Okay. There we go. It is 291.67 ohms. There we go. So this is our potential. Good. So this is our potential. Now, let's go back to our picture. So now that we know that potential, we also know that that potential is the same potential which is across resistor 2, and we know that is also the potential which is across resistor 3. So now that we know those resistances, R2 and R3, and we know the potentials across each one, we can then determine the currents. So let's do that. So finally, we can say is by Ohm's law, current 3 is then equal to what? Potential 2, 3 divided by resistance 3. Simultaneously, current 2 is equal to potential V2, 3 divided by current 2, or sorry, resistor 2. So plug in our numbers, we find in this case then is the current across the third resistor is 0.072 amps, and the current flowing through the second is 0.101 amps. Okay. Now at this stage, a good place or good thing to do is check. Okay. Now it has to be true, let's go back to our picture, is that the current which is flowing through R1 must be equal to the sum of the two currents flowing through R2 and R3. Because the current which is coming through here has to split off, or part of it has to go through R2, the other half or other part has to go through R3, but they have to recombine back together to go to the same current which actually went through R1. So what we should do then is check to make sure that current I1 is equal to current I2 plus current I3. So current I1 was 0.173 amps, and that's equal to 0.101 amps plus 0.072 amps, which in fact is equal to 0.173 amps. So this is true. Okay, so a good thing to do at this stage is just to check to make sure that the potential, or in this case, the currents, sum together. Another check we can do is to make sure that the potential across R1 here plus the potential across R2, 3 is the sum of that of the battery. So it's another good check we can do as well. Okay. So good. So the next part of the question then says, okay, what is the power delivered by the battery? So what's the power delivered by the battery? Well, we now know that power by any electrical equipment is then equal to the current times the potential, right? So in this case, this is going to be equal to the current coming out of the battery, which is IEQ, times the potential from the battery, which is simply the potential from the battery. So this is then going to be equal to 0.173 amps times the potential across the battery, which is 120 volts. So pulling in our numbers, this works out to be 20.819 watts. So the power, which is being supplied by the battery, is then equal to 20.819 watts. Everybody's doing okay? The next part then says, well, how much power then is radiated by each one of the wires? Well, we also know then that the power lost by a resistor is either equal to the current squared times the resistance, or that's equal to the potential across the resistor squared divided by the resistance. Either one is equivalent. Doesn't matter which one that we actually do. Here, what we actually calculated for both of the two different resistors was the current, so let's use this one. So this one means then is that the power lost by resistor 1 is then equal to the current going through resistor 1, which is current I1 squared, times the resistance of that resistor, which is then R1. So this is going to be equal to what? 0.173 amps squared times the resistance, which was 400 ohms. Plug our numbers. This is then 12.04 watts. Okay. So in this case, it's radiating away. So this is the amount of power lost, 12.04 watts. Okay. Power radiated by the second one, then is going to be the current going through the second one, which is I2, times the resistance of that resistor, which is R2. So this is then going to be 0.101 amps squared times 500 ohms, which then is equal to 5.121 watts. And then the power from the third one is then equal to I3 squared times resistance R3, which in this case is then equal to 0.072 amps squared times 700 ohms, which then works out to be 3.658 watts. Okay. Now, again, as a check, what has to be true then is what? The sum of these three power losses, at least the rate at which the power is being lost, must equal the power which is being supplied by the battery. So in this case, my 20.82 must be equal to the sum of these three things, which it is. Because again, 12 plus 8 is 20, plus whatever these remainders are, gives exactly the same thing. So again, what we have to have is that the power gained, or the power from the battery, must be equal to the power from the first plus the power from the second plus the power from the third. Good. Anyways, okay? So again, the way that we do these, again, is exactly the same way that we do those for the capacitors. So again, draw your circuit, identify what is in parallel, what is in series, collapse them. Every time you collapse them, draw a picture of how you went from one to the other one. Get finally down to your equivalent resistor, find the equivalent current, go backwards, unravel what it was that you just did, using what you know is the same based off of where you came from. Again, REQ came from two things in series. What's in series is the same as the current. R23 came from two things which were in parallel. What's the same in parallel? The potential. And then it's just complete applications of Ohm's law over and over and over and over and over and over again until you can't stand Ohm's law anymore. So that's about it. So the next thing we want to look at is, well, what happens if our circuit has more than one battery now? So what happens if, let's say I give you a circuit that looks something like this. So let me put in a battery here. Let's call that EMF1, connected to an internal resistance. Let's call that little R, connected to, let's call that a resistor R4. This one comes around this way. This guy then is connected to R1, connected to R2, connected to a second battery. Let's put the battery going in this direction. So this is EMF2. So this is positive, negative, R1, R2, connected then to a final leg up here, this guy. So this is now R3. So the new question is, okay, so we've now seen how to add these guys in parallel and series with one battery. But what happens now if I start adding in multiple batteries? So now I have, instead of one battery, I have two batteries. So the question becomes a lot more complicated because now I can't say, in this case, that resistor R3 is in parallel with R1 and R2 because that's no longer true. Because R3 is in parallel with the sum of R1, R2, and the battery. So that means all the potential drop across this portion of my circuit has to be equal to the potential drop across this entire leg of my circuit, which includes the battery. So I can't really say this guy is in parallel with these two anymore because that's not really true. I mean, I could still say that these two are in series. That's true. I could say that these two are in series. That's true. But can I say that this guy's in parallel with these two, or that these two are in parallel with this guy, or these two are in parallel with these two? The answer is no, I can't really do that anymore because, again, what has to be true is all the potential across here must be equal to all the potential across here, which must be equal to all the potential across here. So now it's not as straightforward anymore on what is in parallel and what is in series. So I can't really use those laws anymore that we just talked about because now it's a little bit different. So to deal with something like this, we have to introduce new things. And we're going to introduce is what's known as Kirchhoff's rules. Okay. So Kirchhoff's rules basically come down to two rules. Rule number one is what's known as the loop rule. Is actually just equal to conservation of energy. So what this says is if I start off at a point on a loop and I go around that loop and I come all the way back to that same point, then the change of potential has to be equal to zero. Something we've already seen in lab, we've talked about it before. So all this thing says is that the change of potential around a loop must be equal to zero. Right? So this is around a closed loop. This is rule number one. Rule number two, which is also known as the junction rule, which is actually just equal to conservation of current, says that at any junction or at any node, what has to be true is I have to have the amount of current coming in that I have going out. So all this says then is that the sum over the currents coming in must be equal to the sum of the currents coming out. So these are Kirchhoff's loop rules. So the loop rule says that the change of potential going around a single loop is equal to zero, and the currents going in must be equal to the currents out. So basically meaning that if I was looking at this junction, say this junction here, or this junction over here, I can't have all currents going in. So for example, if I call this I1 going in this direction, I2 going in this direction, and I3 going in this direction, I have all currents coming in, no currents coming out, so this cannot be allowed. This is going to overload my system, and then bad things are going to happen. It's basically going to explode, right? So this scenario here is not allowed. So what would have to be true is that I would have to have, for example, let's say I2 coming in, I1 coming in, and then I3 leaving. This is something which is okay. This is conservation of currents. Now, Going along with Kirchhoff's loop rules are also a handful of sign rules. So let's talk about the sign rules. We've already seen the first one. I'm just going to write it down again just for completion. But this deals with a resistor. So if this is point A, this is point B, and let's say my current is going from A to B. So what this says then is if I go in the direction of the current going from A to B, so in this case, I'm going across my resistor in the same direction as the current, then the potential drop going from A to B is then equal to negative the current times the resistance. But if I go the opposite direction instead, so if I go from B to A, I mean, if I go through my loop in the opposite direction of the current, in this case, my potential going from A or B to A then is equal to a potential gain equal to the current times the resistance. The next deals with batteries. So here, if I have a battery, so in this case, if A is on the negative side and B is on the positive side, meaning we're going to go across the battery from the negative terminal to the positive terminal. In this case, I have a potential increase going from A to B, which is equal to that of the EMF of the battery. Okay. But if we go in the opposite direction, so if I go from the positive terminal to the negative terminal, here we go. If I go from the positive terminal to the negative terminal, in this case, I have to have a potential drop equal to that of the EMF of the battery. Okay. The last one is finally for capacitors. We'll deal with these a little bit later. But if I go from the positive plate to the negative plate across the resistor, across the capacitor, so if this is A and this is B, in this case, if I go from the positive plate to the negative plates, in this case, I have to have a potential drop. So in this case, my potential going from A to B is equal to minus the capacitance or the charge divided by the capacitance. But if I go the opposite direction, if I go from the negative plate to the positive plate, we have to gain potential. So in that case, VAB is equal to positive Q over C. Okay. So the way Kirchhoff's loop rules work is you basically have to use those two rules, so the junction rule and the loop rule, along with these sign conventions in some sort of circuit. Okay, so let's talk about how this actually works. So let's go back to our beautiful circuits here. So let's redraw this guy. So again, here is EMF 1 connected to little r, connected then to R4. And then here I had R1, R2, battery in the opposite direction. And then R3. Okay. So let's say I simply give you this guy and then I tell you certain things like what EMF1 is, what little r is, what R4 is, what R2 is, what R1 is, what EMF2 is, and what R3 is. So let's say I tell you all these things, and then I ask you a simple question like, what's the current? What are the currents flowing through each one of the resistors? Now, the way Kirchhoff's loop rules work is, first of all, we have to identify how many loops we have in our system. Now, here, if we count the number of loops, we have the loop for the top loop, we have the bottom loop, and then we have the loop for the entire system, so this outside loop. Now, the way Kirchhoff's loop rules work is that not all of these loops are actually independent, meaning that this inside loop here, the top one, the inside loop here, and the bottom one, and the big one is actually a linear combination of the two small ones. So meaning that this big loop is not independent from each one of these two small loops. So here I have a small loop, here I have a small loop, but the big loop is a linear combination of these two loops. So in general, what's going to happen is, since not all of these are independent, I have n minus 1 independent number of loops. So typically we're going to have n minus 1 independent loops. So here, it looks like I have 3 loops. I have the big loop, the 2 small loops, but not all of those loops are independent. So typically I would have to choose 2 of these loops. The other thing is the junction rule says that this junction here, I have currents coming in, currents going out. This one I have currents coming in and current out. But again, this one is not independent from this one. They're actually redundant. So because the currents coming into this one and the currents leaving is exactly opposite on this side. So the currents coming in is equal to the currents going out. It's just negative of this one over here. So what that means then is that the junction rule, I also typically have n-1 number of independent junctions. What is going to happen though is my loops, the number of independent loops plus the number of independent junctions will equal the number of currents that I have through my system. So how many currents do I have in my system? Well, this part here, all the way through down to this part, everything here is in series, which means everything that goes through this portion all has to have a single current. So all this here has a current. This portion here, since all of these are connected in series as well, this also has an independent current. And then this portion down here, since everything connected down here is also in series, all of this actually has an independent current as well. So that means for this loop, I have 3 independent currents. I have 3 loops, not all of them are independent, and I have 2 junctions. So if I get rid of my dependent loops, I then have 1 loop, 2 loops, 1 junction, so I have 3 equations with 3 unknowns. So basically, what Kirchhoff's loop rules are going to do is it's going to give you the number of equations that you need to be able to solve for the number of currents that you have. So in this case, I have, again, 2 loops, whether I use the big one and 1 small one, or use the big one and this small one, or this small one and this small one, and then use this junction or this junction, but I have 3 equations. I then have 3 unknowns since I have 3 currents, okay? So let's talk about steps. Good. So step number 1, we're going to identify which loops we're going to use. So in this case, I then have what? 3 loops. I can only use 2 of them. So I'm going to use this loop here and this loop here. Okay, so this is step number 1. Identify which loops I'm going to use. Step number 2, choose directions of currents. So what does that mean? So what that means is even though I have a current here, which I drew in the red, I have a current for the blue, I have a current for the green, but we now know a current flows in a particular direction, which usually goes from the positive terminal to the negative terminal. Now, when it comes to Kirchhoff's loop rules, it doesn't matter if I choose the correct direction of the current or not. So here, if I arbitrarily say that this current goes this way, let me draw that in green like I had it before. Sorry about that. Let's get rid of you. So I could say that this one goes this way. So let me call that I1. I could have another current here because this battery is forcing it to go this way. I could call that one blue. I could say this current is going this way. As long as the direction of this one that I choose, since there's no battery up here, satisfies my junction rule, it doesn't matter the direction in which I take it. So that means up here, I can either say that the current is either going into the junction or going away from the junction, but I have to make a choice. I have to choose that my current is going one way or another way. And the reason for that is, if we go back to all of these rules, how I go across it in relation to the direction at which the current is going will either give me a positive drop or a positive increase or a negative drop. So I have to choose a direction. But again, do I have to choose the right direction? And the answer is no. The only thing that's going to happen is you're going to get a negative sign at the end of the day. What does the negative sign mean? It just means I chose the wrong direction. But who cares? Okay? It doesn't really matter. But I have to make a choice. The only choice I have to make, it has to satisfy the junction rule. So it just means that I can't choose all my currents going into a junction because that doesn't satisfy my junction rule. I just have to make sure that at least one of them is leaving. So here we just have to choose the direction of our currents. Once we do that, step number 3 is we then have to choose a direction at which we're going to go around our loop. So we can either go around the loop in a clockwise direction or in a counterclockwise direction. Typically, I'm going to choose that direction to go in the direction of the currents. So if I go in the direction of the currents, that way every time I go across the resistor, I know it has to be a potential drop. If I go in the opposite direction of the currents, it then has to be a potential increase. So, but here, step number 3 is then choose a direction to go around. Oops, I have to write this up here. Direction to go around the loops. Again, does that direction matter? The answer overall is no, it doesn't matter. But I just have to make a choice. All right. So in this case, I can say, well, I'm going to go around this one in this direction, and then I'm going to go around this one in the, I don't know, say opposite direction. So I'm going to go this way. Once I make that choice, I'm then going to use my loop rule and junction rule. So the next step is then step number 4, apply the loop rule. Step number 5, apply the junction rule. Step number 6, solve. Okay. From here, you're just going to solve for whatever quantities that it is that you don't know. Okay. Now, we're out of time, so I can't really do that now. So we're going to do tomorrow, when we're back in class with each other, is to draw a few of these different loops, get practice on how we're actually going to do that. So we'll go around the loops, see how all this stuff works, and then we'll solve some systems, okay? And then I'll start teaching you how to actually do some linear algebra and stuff as well, okay? So we'll do that tomorrow. So anybody have any questions at this stage? So again, we'll apply all these steps tomorrow. We'll go through all the steps. We'll do all the Kirchhoff things tomorrow. But does anybody have any questions on anything else we talked about? Everybody's doing okay? All right. So, good. All right, so I'll see everybody face to face tomorrow. Life will be good. And yeah, have a good day, everyone.
Wait, Dr. Greenwood, I actually do have a question
Yep.
I thought about now. Will you tell us the direction of like the resistors, like going from negative to positive, like in which direction they're going? Does that make sense?
Well, resistors don't have a direction, so there's never a positive or a negative on a resistor.
Yeah, but like.
That depends on the direction of the currents.
Yeah, that's what I'm saying. Like.
No. So that's what I'm saying here is you choose the direction. So you're the one in charge of which side is positive and which side is negative. But what I will tell you is which side of the battery is positive and which side of the battery is negative.
Okay.
So that much I will tell you.
Okay.
But no, so.
Okay, yeah, never mind. I'm just trying to think of it because this is like, in circuits, it's called the KVL.
Okay.
Kirchhoff's voltage law. And like, I'm trying to think of how to do mesh analysis with it.
Okay.
And it's confusing because you're not telling us like the directions. So
Correct.
I just wanted to make sure. So I could just pick what I want to do as long as they match. You know what I'm saying?
Yeah, as long as you're consistent, everything will work out just fine. Yeah.
Okay.
Yeah, so that's why you just make the choice saying, for example, you know, let's say your current's going this way. So that way, if you go across the resistor in the same direction as the current, this has to be the positive side. This is the negative side. So in that case, you have potential decrease of negative I times R.
Yeah, so, it's just like the way the loop enters, like if it enters the negative side of like the battery, then it's a negative voltage, or if it's a positive current, you know what I'm saying? Like. Right.
But again, you're going to be the one who decides that.
Okay.
Not
I just want to make that clears up. I think I can solve it now.
Okay. That's right. So yeah, so as long as you use all of your sign conventions appropriately and just be consistent as you go through, again, the only thing that's going to happen is at the end of the day, you might get a negative I1, but that just means the current was actually going in the opposite direction of what you chose.
Okay.
But that's fine.
Yeah.
Nobody cares.
All right. Thank you.
You're welcome.